If I've got two complex numbers, Z1 and Z2, that are written there, we know from before that the mod of Z1 is R1 and the argument of Z1 is alpha. Similarly, mod of Z2 is R2 and the arg of Z2 is beta. What happens if we wanted to multiply those two complex numbers together? And then when we get the final answer, we can have a look to see what happens with the mod and the argument. So multiplying those two numbers together, the r's multiply together, but so do the two brackets. So I need to multiply cos alpha plus I sine alpha and cos beta plus I sine beta together. Leaving the r's out the front, I end up with the first two, the outer two, the inner two, and the last two. Tidying that up a little bit, getting the real bit first, so I've got cos alpha, cos beta, which is that one. Then this one, because it's I squared, it becomes minus sine alpha, sine beta. Then plus the imaginary part, here I've got cos alpha, sine beta, and sine alpha, cos beta. Now, if you remember your trig expansions, this first one here, cos alpha cos beta minus sine alpha sine beta, is exactly the same as cos alpha plus beta. And then this second expansion here, cos alpha sine beta plus sine alpha cos beta, is your sine expansion for alpha plus beta. So having a look at the modulus, the mod of Z1 times Z2 is going to be R1 times R2, and the argument is alpha plus beta. So just writing that out, the mod of Z1 Z2 is R1 times R2, which in effect is the mod of Z1 times the mod of Z2. Having a look at the argument of Z1 times Z2, it equals alpha plus beta, which is in fact the argument of Z1 added to the argument of Z2. So if we have a look at an example here, if I have 5 cis 2 pi on 3, and I want to times that by another complex number 2 cis 5 pi on 6, I don't have to write it in the other form and then work it all out. I can just use my formula from above. So 5 times 2 is going to be 10, and then it's going to be the cis of, this time I want these two angles added together. So if I have 2 pi on 3 plus 5 pi on 6, so that will equal 10 cis, adding those two together, I get 9 pi on 6, so 3 pi on 2. But that's outside of where we need it, because remembering we start from the positive x-axis and we either go pi radians that way or pi radians that way. But this 3 pi on 2 is to there. So I need to change it to the angle coming back the other way. So that's going to be 10 cis minus pi on 2. And that's the answer. If I have those same two complex numbers and I want to have a look at what happens when I divide them. So I end up with R1 cos alpha plus I sine alpha, brackets, all over R2 cos beta plus I sine beta. Now, if I want to have a look at these, I need to multiply that fraction by the complex conjugate of the denominator. So it'll be cos beta minus I sine beta. Then with my r's, the R1 on R2 just stays there. Then if I expand the top one, the first two, the outer two, the inner two, and then minus I squared is plus sine alpha sine beta all over. When I expand that one, difference of two squares, cos squared beta plus sine squared beta. So, equating the real and complex coefficients, I've got cos alpha cos beta and sine alpha sine beta. So that is the same as cos alpha, cos alpha minus beta plus I sine alpha minus beta. So here, if I want the mod of Z1 over Z2, it becomes R1 over R2, which is the mod of Z1 divided by the mod of Z2. And my angle, so my argument of Z1 over Z2 is alpha minus beta, which is the argument of Z1 minus the argument of Z2. So for example, if I have two complex numbers, 6 cis pi on 2, and I want to divide that by 3 cis pi on 3, divide 6 divided by 3 is 2, and then my angle is going to be pi on 2 minus pi on 3. So my answer is 2 cis pi on 6. So just summarising what we've done so far. If I've got z as a complex number which equals x plus iy, mod z is the square root of x squared plus y squared. But that is also the same as multiplying z by its conjugate, which then is the same as z times z bar. So the interesting thing about that is mod z is the square root of z times z bar. So just squaring both sides, the mod of z squared is the same as z times z bar. Also, if I've got the reciprocal of z, 1 on z, to realise that one I need to times top and bottom by z bar. So I end up with z bar on z bar. So therefore 1 on z equals z bar on, and from before we worked out that z bar was mod of z squared. So we've got that relationship as long as z doesn't equal 0. And also looking at that, if I write it in mod arc form, that is the same as r outside of cos theta, not plus this time because it's z bar, cos theta minus I sine theta, and then z bar squared is r squared. The r's cancel, so we're just left with 1 on r cos theta minus I sine theta, which equals 1 on r. Because I've got this minus sign in the middle here, that's not how we like to have it, so I could change that to a plus, and that's the same as I sine of minus theta. And with cos, it's exactly the same as cos of minus theta. So I can do that in replacing the minus sign with the plus, and the thetas with minus theta. Which then means if I have 1 on z and I want the mod of 1 on z, it's going to be 1 on r, and my argument of 1 on z is going to be minus theta. So from there, if I have the mod of 1 on z, that is exactly the same as 1 on mod z. And the argument of 1 on z is the same as negative arg z. And that's a good relationship to know.